Okay, so what I'm going to do is go through parts of the chapter 12 of the 5 Steps to a 5, which deal with circuitry things. I found a good visual for this, which is I inserted in the second page of this chapter. So again, hopefully you have your own 5 Steps to a 5. If not, follow along. Basically some ideas about how to solve for circuits, dealing with things that are ideal situations and non-ideal situations, dealing with bulbs, resistors, capacitors. Here's electricity explained. Kind of fun. Look, the voltage is like electrical pressure. It's pushing the current through. Resistance is essentially trying to prevent that from going through. So I think that's kind of cute. Oh my! Trying to prevent electricity from flowing. All right, so these are the formulas on your formula sheet in electricity and magnetism. They're of primary importance. There are some others, by the way, but these are the ones that relate with circuits. Electric fields between the plates of a capacitor is less common than most, but if we talk about this when we get to electrostatics, which is our next week's topic, one of the things I think is going to be important is going to be that we look back at the circuitry lab we had with capacitors, so something kind of useful. Current, rate of flow of charge per unit time. So normally you have something like this. Oftentimes we draw schematics instead of a battery, but by convention we think of current leaving the higher potential going to the negative or lower potential. That is conventional current. If for any reason something in the AP exam talks about electron current would be negatives flowing the opposite way. Technically it is electrons that end up being the charge carriers in metals, but by convention we tend to think of positives. This deals with resistivity. This is a really good concept in terms of thinking about how to interpret a graph, perhaps. So, and what factors might affect aspects of the resistance of a wire. So the longer the wire it is, the more resistance. The higher the resistivity, which is this thing, the more resistance. The bigger the cross-sectional area, less resistance. Now, funny thing, I actually have a simulation where I can show that, which I'll do right here. Except my computer is being very slow today. It's kind of being slow every day, I suppose. So we'll go through to that. So, like we said, this is kind of like the push. Oh, there it comes. Wow, that is slow. I do not think this is going to work. It's in circuits. So there's a fun one here with resistance in a wire. There's not much that happens with it. You can see how these factors affect it. Ooh, that's exciting. So notice that. Oh, so it's kind of showing that it's a more dense material with a bunch of stuff that the charge carriers have to go through. High resistance with high resistivity, low resistance with low resistivity. Notice what's happening in here. Long wire, more resistance. Short wire, less resistance. It's like the worst percussion instrument ever, Ben Miller. Oh my. So you can take a look here. FET Colorado Sims, resistance in a wire. I think Ben needs to make a concert about some of this stuff. Okay, we'll go back from that. There's another one related to Ohm's law, which is kind of fun. Does the same sort of thing. More push caused by higher potential difference. More current. Less resistance. I wonder if we can get all three of these to be the same size. No. Okay, never mind. Goofy. Back to this. So that's Ohm's law. That's the power formula. Notice that the power formula, V delta V times I, if you substitute in Ohm's law, so for example, delta V over R for current, you get delta V squared over R. If you rearrange this and say V equals I times R substituted in here for V means I squared times R is equal to power. The reason that can be important is because you do want to recognize that as the current through a circuit doubles, the power rating will quadruple, which means it'll get very hot. It'll get 4 times as hot, actually. Down here, this is a really good page. I look at this on page 165, making sure you understand the difference between ohmic and non-ohmic materials. So something's ohmic when it maintains the same resistance under different conditions. Oftentimes, things are non-ohmic if the temperature changes between them. But this gives a really good explanation of that. This page was done really well, I thought. Resistors in series and parallel. Well, here's the schematic symbols. A switch is something that you can see often as like a line and then another line broken away from it. So series circuit, current's the same everywhere. The voltage across each resistor adds up to the total voltage provided in the circuit. Parallel circuits, here, the voltage across each branch is equal to the total voltage provided in the circuit, and the current through each branch, so the current through here plus the current through here plus the current through here would equal the total current leaving the power source. So one of the things you got to be careful of is understanding that a battery doesn't provide charge, it provides energy, and that energy pushes the charge. That's what the potential difference is, energy per charge. So here's the rules for series and parallel circuits. They go through talking about this chart a lot. And I essentially do things like this, but I haven't ever necessarily set it up as a chart. They talk about why that might be important. I think on this year's AP physics exam, with there being fewer calculations and more conceptual explanations, I don't necessarily think that the chart is that important, but I do think you need to understand what happens, say in a circuit like this, for example. So you need to recognize that the total current here is going to be more than the current through this branch or this branch, but that these two currents would add up to the total. You should also recognize that the current through this bottom branch would be less than the current through the top branch because it has more resistance. So again, this is a combined circuit, and if they have circuits on the AP exam, they tend to not have ones that are super complicated. But my bet is they wouldn't have one just with resistors. They would probably have one with resistors and capacitors. So they take several pages here to go through this VIR chart. I don't think it's a bad idea to do that, just to make sure you understand it. They round off a little more than I would here, but they talk about how do you know what the voltages are and how do you attack which part of a circuit to solve. So, and I don't think that's a bad thing to understand. So they talk about tips like this. One of the things that's nice, and this person says this here, seems like an awful lot of work for a simple problem. It is, but by doing something like this or thinking about what happens in each part of a circuit, you could really answer any question about it. So Kirchhoff's rule, there's a loop rule and a junction rule. The junction rule says that the current entering a junction has to equal the total current leaving a junction. The loop rule says that in any loop around a circuit, the net voltage is 0. So in other words, if we're crossing this battery, we gain voltage, we lose some across this resistor, we lose the rest across that resistor. That's one loop. The other loop is here, we gain voltage across this, lose some across this, and for certain charges that go on the top, we would lose the rest of the voltage across that. So they're called the junction rule and the loop rule. Junction rule is basically amount of material in equals amount of material out. It's conservation of matter. The loop rule, the energy provided is all dissipated, is basically conservation of energy. I don't think you're going to see circuits with two power sources in them. I don't think AP2 is going to do that. I've never seen that. It is an AP Physics C, however. They go through a lot of examples here. Ranking tasks, probably a good thing to know. So you may want to look through some of the conceptual questions that we did with circuits, which is in the chapters like 25-ish, something like that. Maybe a little higher than that in your textbook. Brightness of a bulb, I think that's actually really important to be able to rank those also. So the brightness of a bulb depends only on the power dissipated. So that's I squared times R, V times I, or V squared divided by R. So if you remember when we did that light box activity, we noticed that the light bulbs that were brightest in a parallel circuit were the dimmest in a series circuit. Why is that? Well, the light bulbs that were, normally we have light bulbs in parallel circuits. And so if we have parallel circuit, the brightest bulb is the one with the least resistance because it allows the most current to go through it in the same voltage, since voltage is the same across all parallel circuits. In the United States, that's around 120 volts. But what that now means is if we put a series of bulbs in series, rather, the bulb with the most resistance is going to take the greatest voltage to overcome that resistance to have a constant current in a series circuit. So the bulb with the least resistance would actually dissipate the most power in a series circuit. So when things are rated at a certain power rating for bulbs, that's based on 120 volts. I think the thing with this is that rating is only for parallel circuits. So big idea, resistance of the bulb is the property of the bulb itself. Hooking up ammeters and voltmeters is really important to understand. Voltmeters are hooked around or across objects where you want to measure the voltage. Why? Because voltage is the same in all parallel parts of a circuit. So if you hook a voltmeter up in parallel with what you want to measure, it will have the same voltage across the voltmeter as it does across those objects, or potential difference. Ammeters have to be hooked up in series. So in this case, this ammeter A1 would measure the current, the entire current of the circuit. This ammeter A2 would measure the current only going through this branch of the circuit. And we could predict the current going through this outer branch by taking the total, subtracting the current through this middle branch. So they talk about internal resistance of a battery in here. Terminal voltage is equal to EMF minus current times the internal resistance of the battery. So we did a lab with that, one of our circuitry labs first semester. I would go over and look at that part because I think a very good AP question they could ask this year would be something about giving you a scenario, maybe a graph, something like that with voltages and currents and asking you to determine the resistance and then saying, well, now assume that the battery is not ideal and has significant internal resistance. How would this affect? And they could ask some different things about it, like how would that affect what you determine the resistance would be outside of the circuit or outside of the battery itself. So I would definitely go back and look at that lab. I can take a minute and see if I can figure out which one that is. Is it on here? Which one was that? Circuit lab. Circuit Jamboree, Circuitry Lab. Why do I not find that? Circuit Lab. Oh well. I don't know where it is. Dang. Meters ammeters and batteries. Let me check something here. Oh, that was this year, wasn't it? Capacitor lab. And once again, it's thinking a long time about it. God, that's freaking great. Forgot this computer has an older version of Microsoft Word, because of course it does. I'm just going to go back here and it'll probably open at some point. Okay. There we go. So there's this circuitry lab. And actually it was 1920, it says that. So the first part was the one with capacitors. The last part of this lab is the part that I think dealt with, nope, never mind. I can't find it, but I will look for it at some point. Okay, so switches in a circuit. So you do want to understand what happens when you open and close a switch. We normally didn't use those in our labs because we just connected or unconnected things. So for example, if you have this circuit and the switch is open, it's a series circuit. If you close it, it's now a combined circuit. And that does change everything, because if we close this, we overall lower the total resistance of the circuit. That means the total current would increase. That means the voltage across that bulb with a constant resistance would change. And actually that's kind of an interesting thing, that just changing one part of a circuit really affects all parts of a circuit. So they go through that example here, and this is page 177. Capacitors, pretty important. So I am pretty sure that whatever circuit you see might have a capacitor in it, or would be likely to. So capacitor is something that can store charge or hold charge. There are two real formulas for capacitance. C equals Q over delta V, or C equals K epsilon 0 A over D. So this is a constant, 8.85 times 10 to the 12th, area of one of the plates, distance between the plates in meters. Dielectric, we did talk a little bit about dielectrics and how they can increase the capacitance and why they can increase the capacitance of a circuit. I remember doing notes about that on the board. And in general, capacitance is charge held per voltage. So if you have a certain capacitance and then you up the voltage, you would also up the amount of charge that would be held. If you have less capacitance, at the same voltage, you would hold less charge. So it's really a ratio between these things. There's other things about energy stored on a capacitor, and that depends on the voltage across it and the amount of charge that's held. So the way that you get these two are equal to each other is this delta V is equal to Q over C. So C delta V squared is the same thing as Q delta V. Okay, that makes sense to me. Because Q is equal to delta V times C. So that's how you get the V squared. That's the most common way I've seen of figuring out energy stored in a capacitor. This is electric field strength on a capacitor. I'm not going to talk about that much. Parallel and series capacitors are definitely something you should know how to solve. I can easily see a circuit where you have a capacitor in one part and resistors in other parts of the circuit. Asks you about what happens both when a switch might be closed immediately as well as when a switch might be closed after some amount of time later. So I would look at this particular example, this part of your 5 steps to a 5 for sure. Big idea, capacitors in parallel have a greater capacitance. So this would be a capacitance of 6 microfarads instead of 4 or 2 microfarads. Capacitors in series you have less total capacitance. And the reason behind that is that the charge on each plate of the capacitor has to be the same, and it's the same, but the voltage is split across those. So here, the voltage across this is 200 volts, the voltage across this also 200 volts. So it's basically acting like one larger capacitor with a bigger plate area. If you have capacitors in series, hopefully they have a diagram about that. Well, of course they don't, but this is probably a good one to think about. But basically what you end up having is less total capacitance because the voltage is split across the capacitors. So they do go through some of these charts here and examples. I would draw them out. I don't know why they didn't draw it out for you. And then a circuit like this where you've got several capacitors, what I do first is I do 1/6 plus 1/3, and essentially that should give me 1/2. So the capacitance of this branch is 2 microfarads, and then I'd add the 2 and the 4 since they're in parallel. That would give me 6 microfarads. And that would overall tell me how much charge can be held. Easy peasy lemon squeezy. That sounds kind of naughty. This is the type of thing that I could see. So I would recommend going through this type of example and thinking about what would happen just when a switch is closed as well as when a switch would be opened. So essentially, when this switch is closed, this capacitor initially, which would have no charge on it, acts like zero resistance. After a long time, it's going to act like an infinite resistance, and that basically turns this thing into a series circuit. Yeah, they do take a couple pages to go through that. I would really encourage you to look at that, these examples, and then they go through practice problems at the end of the chapter. The answers are toward the back. Of those, and they give good explanations as well.